we're going to talk about composition of functions. When we're looking at composition of functions, we have this notation that we use here to talk about our composition of functions. The way that we verbally say this is f of g of x. We don't say fog of x. Okay? What this means is that g of x becomes our input for f of x. Okay? And our domain for f of g of x is all of the domain for g of x, and also for our f of g of x. So you have to check two domains, the g of x and then your final answer of f of g of x. And you got to check the domain for both of those. Okay. So for example, if we have the equation f of x equals x plus 2, and we have g of x equals 4 minus x squared. When I want f of g of x, we're really thinking, okay, we want f of g of x like this. I like to rewrite it like this because it seems more obvious that the g of x is the input. Okay. So what I'm going to do is I'm going to put g of x as the x value for our f of x. So what I like to do is I take the outside one and I write the function x plus 2, but instead of putting x, I just put sets of parentheses. So I have the x plus 2 here and it's x plus 2. Now instead of the x, I'm going to plug in the entire thing of the 4 minus x squared. So I'm going to do 4 minus x squared. So we've got, this is the f of x, but we're inputting the g of x into the f of x. Okay? So then what I do is I simplify from here. Now there's nothing that needs simplifying inside the parentheses. There's nothing to do outside of the parentheses, multiplying or dividing. I just have an add 2. So that means that the 4 and the 2 are like terms, so that gives us 6 minus x squared is our f of g of x. Now, if I were to look here at what our domain is, I would have to look at the domain of g of x. Our domain for g of x is a parabola. There's no restrictions with a parabola. If I look at our f of g of x, there's also no domain restrictions because this is also a parabola. So I have no domain restrictions, so our domain is really negative infinity to infinity for f of g of x. Okay. The reason you have to check g of x is because if there's a domain problem of g of x, when I try to put it into f of x, it will cause a problem. So that's why you have to check f of x as well as your f of g of x. Okay. Now, if we look at g of f of x, you can go the other direction, which just means that now f of x is the input and g of x is the output. Okay, so I'm going to start with my g, so that's the blue one. So I'm going to write that one, and just instead of writing x, I'm going to put parentheses. So quantity squared. So we've got this is our g of x, and then in place of the x, I'm going to plug in the f of x, which is x plus 2 in this case. Okay. So here, when I plug this in, we have to square this first, then times by this negative, and then add the 4 to it. So remember, when we square a binomial, you square the first. So if I square x, that's x squared. You square the last, so we square 2, which is 4. And then you do twice this product, which is 2x. So we get 4x in the middle. Okay. But we are still doing 4 minus this entire thing. So we have to distribute our negative to each one of these. So we get minus x squared, minus 4x, minus 4. But we still have this 4 out in front that we can combine now with this 4. Those go to 0, so we get negative x squared minus 4x. Now notice, f of g of x and g of f of x are not the same thing. These are not equivalent, right? And that's fine. There's nothing wrong with that. We also have a way where we can input one thing into itself. So if we look at this one, this is f of 3. Now I'm going to show you how to do f of x, and then we'll talk about a second way that you can find it when you have a number that you're plugging it in. So I'm first going to find f of x. So on this one, I'm going to write x plus 2 I'm leaving parentheses for my x. But then I'm going to plug in place of the x, the f of x. So we've got, this is our original f. And then, let's see here, do I have, sure we can go, this is the other f that we're plugging in. Okay. So you can plug something into itself, which seems bizarre, but it's something that can be done. So again, there's no simplification with inside the parentheses, so I just combine like terms of the 2 and the 2, so then that gives us x plus 4. Now this is f of x. If we want to find f of 3, that means that I'm just going to plug in 3 into here. So if I plug in 3 into here, that means that I've got 3. No, that's not how I want to write that. I want to write it like this, f of 3. There we go. I do 3 plus 4, which gives us 7. Now, we can also find this a different way. So if we look at this and I write it the way that I just erased, okay, if I find this, that means that 3 is the input for x. So if I plug in 3, that means f of 3 is really 3 plus 2. Well, that gives us 5. So that means that this thing here is really the 5. So then I'm going to substitute in for this f of 3, the 5 in its place. So now I find f of 5. Well, if we find f of 5, I'm going to plug it in for my x value here. So this gives us 5 plus 2, which gives us 7. Which notice, we got 7 when we did f of 3 this way as well. Okay? So you can do either way. Both get you to the same spot. Okay? So let's take a look at some other examples. So if we do g of f of x, okay? So we've got, we'll do f of x is green and g of x is blue again. Okay? So what I'm going to do is I'm going to rewrite this like g of f of x like this, so I can see that the f of x is the input. Okay? So for my g of x, that's really x squared plus 4. So then I'm plugging in place of the x, which I have sets of parentheses, the f of x, which is the square root of x. Well, here, the square root of x squared is just x, because the squared and the square root undo each other, so we get x plus 4. Okay? Now, if we were to talk about the domain restriction for this one, notice on f of x, which is what we're plugging in, that we can't have negative numbers on our square roots. They give us imaginary numbers. So remember that our domain restriction for f is that it has to be greater than or equal to 0, which if you do interval notation, you would write it as bracket 0 to infinity, right? If we look at this final answer for g of f of x, this is a line, so there's no domain restriction for a line. Everything works. However, because we were plugging in f of x and there's a domain restriction from there, I have to carry this for our domain restriction for f of g of x. Or sorry, g of f of x. Okay. If we look at f of g of x going the opposite direction, so we want f of g of x, so our g of x is the input. Okay. So then f is what we're writing first, so I'm going to do the square root of whatever our x is, so that's our x that we're doing, and then we're plugging in our g value, which is x squared plus 4. So here, there's no simplification I can do. Some of you might be tempted to take this as the square root of x plus 2, or take out of the root of x plus 2, but when you're adding two things, you can't just take them out of the root. You need to have multiplying in order to take them out of the root. Okay, so there's not any simplification to this, so our answer is just the square root of x squared plus 4. And this will have a domain restriction. This means that x squared plus 4, we can't have that number be negative underneath. So this parabola, or this quadratic equation, can't be negative. So I would set this greater than or equal to 0, and then we would solve that. Okay? So that would give us our domain restriction. I'm not super worried about the domain restrictions. I just want you to be aware of where they come from. Okay. Now, if we skip down and we look at some of these, and we're plugging in numbers, so let's practice plugging in some number ones. Okay. Now, personally, I think it's easier to do the route where you do plugging in the number instead of finding f of g of x and then plugging in 4 when you finish. So here, I'm going to do f of g of 4. Wow, that was written horribly. F of g of 4. Okay. So g of 4, that means that I'm going to plug in 4 for g. Well, g of x is 3x squared, so 3 times 4 squared plus 1. So if I do 4 squared, remember you have to square first before you multiply, so that gives us 16 times by 3, which gives us 48, plus 1, which gives us 49. So now, the g of 4 is 49, so I'm going to plug in 49 in place of the g of 4. So that gives us f of, but the g of 4 is really 49. Okay? So this y value of the x value, this y value becomes our new x value for the f value function. So now I'm going to plug in 49 for f of x. So then I'm going to do 2 times 49, which gives us 98. Okay. Now you can also, let's do, g of f of 2 on this one. Okay. So that means that I'm plugging in 2 for my x value for f. So if I find f of 2 first, that means I'm really doing the absolute value of 2 minus 2. Well, 2 minus 2 is 0. The absolute value of 0 is 0. So that means that we've got f of 2 is really 0. So in place of this f of 2, I'm going to write 0. So then I now can find g of 0. Well, g of 0 means that I'll do 3 over 0 squared plus 2, which will be 3 over 2. Right? So our g of f of 2 is really 3 halves. Okay? You can also compose with itself. So if we do g of, okay, that's an f. G of 0. Okay. That means that I'm going to plug in 0 for g. So that gives me 2 over 0 plus 1, which gives me 2 over 1, which is 2. So then I'm going to plug in 2 again for g. Plug in again to g, but it's a different number. So then this gives me 2 over 2 plus 1, which gives me 2 over 3. So our g of 0 is really 2/3. Now, we can do the same thing with different representations. So instead of having it from equations, we can have it from a table. But our pattern of how we're doing things is exactly the same. So instead of plugging it into the equation, we're going to use the table to find our x and our y values. So if we look here, and we're doing f of g of 4, okay, so I'm going to go to g of 4. So I'm going to look at what my x value is. So my x value is 4, and we're looking at the g because we're looking for g right here. So at 4, we got 1. So g of 4 is really 1. So I'm going to plug in the place of g of 4, I'm going to plug in 1. Whoops. I suppose I should have color coordinated that. So that gives us f of 1. Well, now I'm going to go to the x value of 1. So our x value of 1 is right here. And we're going to look at the x value on the f of x part. So at 1, we're going to get negative 3. So then this gives us negative 3. Let's try the g of f of 7. So if we do g of f of 7, so we're going to go to the f of x of 7. So 7, our f is 3. So f of 7 is 3. So that means we're now going to find g of 3. So then I'm going to go to the 3, and I'm going to go to g of x, which is 1.5. So our g of f of 7 is 1.5. Now, you can again compose with itself. So if we look at f of 10, that means that I have to find 10 for our value first. So I go to f, so that's 6. So f of 10 is 6. So that means that I'm going to replace the f of 10 with our 6. And now I'm going to find f of 6. So I go to the x value of 6 and I go to f, which is 2. So our f of 10 is really 2. Now we can do the same thing, but it's from our equations, or from our graphs rather. So with our graph here, if we pick f of g of negative 7, so I'm first going to go to the x value of negative 7. So 1, 2, 3, 4, 5, 6, negative 7. Okay, so we're looking at this x value. We want to go to g of negative 7. So g is the green one, so I'm looking at the green graph. So at the green graph, we are at 2. So this point is negative 7, 2. So that means that g of negative 7 is 2. So then here, we're going to plug in our 2, and we're going to go to that x value, and we're going to look at the f value, which is the blue graph. So at 2, we're up at 1. So this point here is 2, 1. So f of 2 is 1. If we look at this one, the g of f of negative 1, okay, we want to look at the x value of negative 1. Now at negative 1, we want to be looking at f. So they cross right here, both of them. I mean, there's still graphs. This would have just had to have been extended, and this would have had to be extended, but you can see both of them on this part. So you want to make sure I'm looking at the f one. So if we look at the f one, at negative 1, that's the blue one, so we're down 1, 2, 3, 4, 5. So this is negative 1, negative 5. So that means that f of negative 1 is negative 5. So now we're going to find what g of negative 5 is. Well, if we go to negative 5, 1, 2, 3, 4, 5, g of negative 5, that's this one. So we go up to here, and that gives us 1, 2, 3, 4, 5, 6. So g of negative 5 is 6. Let's make sure I counted right. 1, 2, 3, 4, 5, 6. Yes. So g of negative 5 is 6. Now, before this, we had been talking about inverses. So what do compositions have to do with inverses? Well, it turns out if you find f of g of x and g of f of x, and both of those things equal our x value, then those two are inverses of each other. So what we can do is we can determine if our equations are inverses based on composing them. Now you do have to compose them both directions. It's not just one direction, it's both of them. It has to be both f of g of x and g of f of x. So for example, if I check this one, f of g of x here, that means that g of x is the input for f of x. So 3 times x plus 2. So in place of the x, I'm going to put x minus 2 over 3. Well, if we start simplifying, notice these 3's can cancel to 1. So that gives me x minus 2, but still plus this 2 over here. While the 2's can go to 0, which gives us just x. Okay? Now, you need all of these steps to show that you got to x. You can't just go here and say that it's equal to x. Even if you can see it, I need the step-by-step process. But we can't just stop and say these are inverses. You have to check the other direction. Just because one is x doesn't mean the other one is always x. Okay? So we do g of f of x, so that means that g is the outside function, so x minus 2 over 3. And then we have to input the f of x, which is 3x plus 2. Okay? So this is all on the top. There's nothing else I can do in parentheses, so these are like terms, so those go to 0. So that gives us 3x over 3, but the 3's can reduce, and that just gives us x. So that means that f of x and g of x are inverses. Because g of f of x is x, and f of g of x is x. Okay. If we look at the next one, if I plug that in, so if we do g of f of x, that means that we're going to do the cube root of something minus 9 over 2. So our something is 2x cubed plus 9. Okay. Well, there's nothing I can do inside the root. You might be tempted to say these are 0, which they would be, except for this one's under the root. Well, I can't take this out of the root. There's nothing I can do. So there's actually no other simplification that this has that can be done. So that's it. This does not equal x. So I can say not inverses. Okay. Now, if perhaps you had tried the other direction first and you did f of g of x. Now, if one of them isn't equal to x, then you don't have to try the other way. I'm just showing you, had you picked the other way, that you would get a similar answer that doesn't simplify to 0. So we would do 2x cubed plus 9, and in place of the x, we would put in the cube root of x minus 9 over 2. Okay. If this whole thing is cubed, that means that I would have to use the binomial theorem expansion, or do this thing times this thing times this thing and multiply it out. If you do your binomial theorem, it'd be 1, 3, 3, 1, and then you would take the cube root of x cubed, the cube root of x squared, the cube root of x to the first, the cube root of x to the 0, and then you would take the minus 9 to the 0, the minus 9 to the first, the minus 9 to the second, minus 9 to the third, and then we'd still need pluses in between here. Obviously, I didn't leave myself enough space. This is not going to simplify down to something pretty. It's going to be quite nasty, right? So there's nothing that I can do that will make this simplify with the 9 to get to 0. Notice if we take this all over, remember when you cube something, it's the top cubed over the bottom cube, so this would be over 8, and then you would be timesing that by 2. Well, the 2 and the 8 would reduce down a little bit, but I would still have this whole thing divided by 4 and then plus 9. It's not ever going to get down to x. So they're not inverses. Okay. So that's what we can do with our composition of functions to help us see if two functions are inverses of each other.